Imagine you're settling into your seat on a flight. You fought your way through security. You finally found a tiny sliver of overhead bin space.
Which is a miracle in itself.
Right, a total miracle. And you're buckling up. Maybe you're starting a movie on that little screen in front of you.
Yeah, you're just getting comfortable.
Exactly. And from your perspective as a passenger, the flight is just, well, a journey from point A to point B. It's just a pressurized metal tube taking you to a vacation or, a business meeting.
But the reality is completely different.
Yeah, because behind that reinforced cockpit door and thousands of miles away in some bustling operations center, there's this massive, intricate web of active flight management happening, like right at that exact second.
And it is entirely invisible to you. I mean, the passenger just sees a vehicle. But the aviation industry, they look at a plane and see a node in this mathematically precise network of risk management.
Right, risk management, which is exactly what we're getting in today. We're doing a deep dive into the operational procedures that keep commercial air transport safe.
It's a fascinating area.
It really is. We're specifically looking at excerpts covering EASA rules. That's the European Union Aviation Safety Agency, from Phil Croucher's Operations and Procedures documentation.
Yeah, these are the documents that basically outline the legal and operational architecture that keeps that node from failing. It's the hard law and the soft law of how you put a plane in the sky, and bring it back down safely.
And we're going to explore how a flight is actively managed from a bunch of different angles today.
Right, because there's so much to it.
Oh, totally. We've got the physical tracking of the aircraft,
Yep.
the biological limits of the human pilots, which is wild.
So FTL rules, yeah.
The flight time and duty limitations, and then the hazards of taking off in terrible weather, and the sheer economics of fuel policies.
That's a lot to cover.
It is. But whether you're, an aviation enthusiast or just a frequent flyer, or even if you're just intensely curious about how massive global systems operate without just falling apart, this is for you.
It will definitely change how you view your next flight.
Well, absolutely. So let's start with the first layer. Before an aircraft even leaves the gate, we have to establish, well, who is actually responsible for it?
Right. Legally speaking, the airline holds the ultimate responsibility. They have the air operator certificate.
Okay.
And regulators require them to establish a concrete system for exercising operational control over every single flight.
So it's not just someone drawing up a schedule and saying, hey, go fly.
No, not at all. It goes way beyond scheduling. The airline has to ensure the flight is conducted under strict provisions. They have an operations manual. They have to make sure the aircraft is equipped for that specific route. And, that the crew is actually qualified.
Right. Trying to visualize that relationship between the airline on the ground and the pilot in the air is kind of tricky.
Yeah.
I was thinking it's a bit like lending a teenager the family car.
That's an interesting way to look at it.
Right. Like the airline sets all these strict rules. They track the car. They pay for the gas. But the teenager, the pilot in command, has the ultimate authority to, pull over if it starts pouring rain and it gets too dangerous.
Yeah, that makes sense. A more traditional analogy is maritime shipping.
Oh, really? Like cargo ships?
Exactly. Because aviation law actually inherited a lot from maritime law. The shipping company owns the vessel, they chart the course, but once that ship is on the open ocean...
The captain is in charge.
Right. The executive sitting in a boardroom in London can't micromanage the rudder during a storm. The captain has to make the call.
That makes total sense.
So in aviation, the airline builds the safe environment, but operational control is delegated. In smaller companies, the chief pilot delegates it directly to the commander of the aircraft or to a flight dispatcher.
And the commander has the final say.
The sole unassailable authority. They decide on initiating, delaying, diverting, or rerouting the flight if conditions demand it. The airline gives the parameters, but the pilot navigates the reality.
But the airline isn't just, waving goodbye and hoping the plane shows up in New York. They are watching it. And reading the manual, the mandates for aircraft tracking have gotten pretty aggressive.
Very aggressive. The European regulators drew a hard line in the sand regarding how aircraft are monitored.
Right. And it's because of those haunting past mysteries, isn't it? When planes just vanished.
Exactly. I mean, historically, tracking a plane over an ocean was incredibly difficult. You relied on high-frequency radio reports, which get lots of atmospheric interference.
Or you just waited for them to pop up on someone else's radar?
Right. But when a large commercial aircraft disappears without a trace, which we've seen happen over the last decade, it exposes a massive vulnerability.
Because you can't search 1 million square miles of ocean.
You just can't. It's impossible to mount an effective search and rescue operation with that much guesswork.
So, They mandated automated tracking. But looking at the rules, there are these really specific thresholds. It applies to aircraft weighing over 27,000 kilograms with more than 19 passenger seats.
Yep, the MCTOM and the MOPSC limits.
Right, those acronyms. But why that specific cutoff? Why not just track every single Cessna in the sky?
It's all about balancing commercial risk against, well, technological feasibility. A 27,000-kilogram aircraft carrying 20 people is a significant mass casualty risk.
Okay.
It's a commercial airliner. But equipping a tiny, private four-seater plane with a highly advanced satellite-linked tracking system,
That would be insanely expensive.
ruinous for the owner and practically unnecessary because those small planes aren't flying transatlantic routes anyway. But for the big jets, regulators mandated systems that automatically determine the location of the end of a flight.
Location of the end of a flight. That is such a sterile, bureaucratic way to say where the wreckage is.
It is, yeah. But the key word in that whole regulation is automatic.
Because the pilots are too busy during an emergency.
Exactly. In a catastrophic emergency, the crew is entirely consumed with trying to save the plane. They are aviating and navigating. Communicating is literally their last priority.
Right, they're not going to stop and text their coordinates.
No. So the tracking system operates independently. It constantly handshakes with satellites, sending position, altitude, heading. And if it detects anomalous behavior like a sudden, drastic loss of altitude, it increases the frequency of those pings.
Oh, wow. So it leaves like a digital breadcrumb trail right down to the surface.
Yeah, precisely. But there are exceptions. Airlines don't always have to use these redundant systems if their route is fully within airspace where air traffic services already provides adequate surveillance.
So if I'm flying from like London to Frankfurt.
Right. You never leave primary or secondary radar coverage. The air navigation providers have you on their screens the whole time.
From wheels up to touchdown.
Exactly. For an airline to run an expensive satellite system over mainland Europe would just be unnecessary duplication. As long as they've given ATC their contact info, they're fine.
But once you go over the Atlantic.
The moment you leave coastal radar, the internal tracking system becomes the primary lifeline.
Okay, so we've got the physical machine tracked, but, the machine is completely useless without the human beings operating it.
Very true.
And getting into the flight time and duty limitations, the FTL rules, it's glaringly obvious that regulators view fatigue as a severe hazard. Like, we're talking about the biological limits in the human battery here.
Fatigue in aviation is insidious. It degrades your cognitive function, your reaction times, and your ability to process complex problems, which is exactly what flying a commercial jet requires.
You don't want a surgeon operating on you after being awake for 24 hours.
Right.
Same applies to a pilot.
Absolutely. So the regulatory framework divides a pilot's time into strict categories to force physiological recovery. And the biggest distinction is between a duty period and a flight duty period.
Yeah, those sound identical to a layperson, but the legal difference is huge.
Massive. A duty period is any time you are doing tasks for the airline. Ground training, paperwork, being on standby, or positioning.
Okay, wait, positioning. Also known as deadheading, right?
Yes, traveling to a location to start a flight.
I have to push back on this because it seems crazy. Let's say I'm a pilot based in London. The airline needs me to fly a jet out of Dubai tomorrow. They put me on a commercial flight to Dubai. I'm sitting in first class, lie flat bed, sleep mask, warm meal. I sleep for 8 straight hours. Why on earth does EASA refuse to classify that as rest? I am objectively resting.
You're inactive, yes, but you are not in a biologically restorative state, at least not according to the regulators.
How so? I'm asleep.
Because real rest requires the complete absence of corporate control. When you're positioning, even in a lie-flat bed, you're traveling at the behest of the company. You're subject to cabin noise, vibration, mild hypoxia from the pressurization. You don't control your environment.
Huh, I guess that's true.
Plus, your stress hormones, like cortisol, don't fully drop when you know you're on the clock, heading toward a high-stakes job. So the regulations draw a hard line. All time spent flying, even as a passenger, counts as duty time.
That is a massive penalty for the airline scheduling department.
It is. In fact, if that passenger flight immediately precedes you stepping into the cockpit, that positioning time counts as part of your actual flight duty period.
Wow. So what exactly defines the flight duty period, the FTP?
The FTP begins the moment you report for a flight, usually an hour or so before departure when you're checking weather and fuel, and it ends when the engines shut down at the final destination. Blocks on.
And what's the maximum limit for that?
The baseline maximum is generally capped around 13 hours, but it's highly fluid. It shrinks depending on your circadian rhythm, like what time of day you started and how many individual flights or sectors you're flying that shift.
Right, because taking off and landing 4 times in a day is way harder than just cruising on autopilot over the ocean for 10 hours.
Exactly. The cognitive load during departure and arrival is immense.
Yeah.
You're talking to ATC, configuring the plane, dealing with weather. Cruise is heavily automated, so EASA aggressively penalizes multi-sector days. If you fly 4 short hops, your maximum legal working day shrinks significantly.
That makes total sense. I was looking at the cumulative limits, too. A pilot is capped at 190 duty hours in any 28-day period.
Yes.
Now, coming from a normal desk job where 40 hours a week is standard, 190 hours in a month actually sounds kind of light. Why is that considered the absolute red line of human exhaustion?
Because sitting at a desk doesn't subject your body to the physiological stressors of a cockpit. You're operating in an environment pressurized to an 8,000-foot mountain peak.
Oh, right. The altitude.
The air is incredibly dry, so you dehydrate rapidly. There's constant low-frequency vibration and background noise that just wears down your nervous system over hours.
I always feel exhausted after a flight, just as a passenger.
Exactly. Now add the cognitive vigilance required to monitor systems where a failure could kill hundreds of people. The mental bandwidth required to maintain situational awareness at 500 miles per hour. You just can't sustain that for 40 hours a week, every week. The 190-hour limit prevents chronic compounding fatigue.
And the airlines can't just game the system by throwing pilots into random shifts to hit those 190 hours. The manual talks about safety management systems avoiding nasties.
Ah, yes. Nasties is a great industry term. It refers to highly fatiguing schedules that are technically legal but biologically destructive.
Like what? Give me an example.
Like giving a pilot a late-night flight, then giving them the legal minimum rest during the day when humans are evolutionarily programmed to be awake, and then giving them a super early morning departure the next day.
Oh, that sounds miserable.
Yeah.
Total circadian whiplash.
Exactly. The safety management system has to proactively prevent those patterns.
Which perfectly leads into acclimatization. Aviation breaks your body's rhythm constantly by dragging you across time zones.
The legal framework here is fascinating because it basically tries to legislate biology.
How does that work?
When a crew crosses time zones with a difference of 4 hours or more, the regulators acknowledge your internal clock is completely out of sync. So for the first 48 hours in the new time zone, you are legally considered to still be acclimatized to your home time zone.
Wait, really? So if I fly from London to Tokyo for 2 straight days, my duty limits are calculated as if I'm still sitting in London?
Correct. Your body still expects to sleep when it's dark in London. But here's the tricky part. After 48 hours, you haven't fully adjusted to Tokyo yet, but you've definitely lost your sync with London.
So what time zone are you in, legally?
You're in what EASA calls an unknown state of acclimatization.
Wow, an unknown state.
Yeah. And during this unknown state, your maximum allowed flight duty period is heavily reduced. The regulators assume you are biologically confused and highly susceptible to fatigue. You only get your full duty limits back after spending a calculated number of days resting in the new time zone.
That is an incredible acknowledgement of human frailty. But I did see a mechanism in the rules that almost looks like a loophole, or at least a very clever tool for airlines to stretch a pilot's day. It's called split duty.
Split duty is basically an economic necessity for certain routes, especially when you fly to a destination, wait around for several hours, and then fly the exact same plane back.
Okay, so how does it work?
If there's a continuous gap between those flights of between 3 and 10 hours, the commander can count half of that gap as rest, and they can add that time to their maximum allowed flight duty period for the day.
So if my max legal day is 12 hours, I fly to Rome, sit on the ground for 6 hours waiting for the return flight. I can take half of that 3 hours and extend my maximum day to 15 hours.
The math works, yes. But regulators don't just let pilots sit on a bench and call it rest. To claim a split-duty extension, the airline must provide what they call suitable accommodation.
And I'm guessing EASA is pretty strict about what that means.
Ruthless. You can't just point to a quiet corner of the terminal or a break room sofa. It must be a private, quiet, comfortable place, not open to the public.
Like a proper hotel room.
Usually, yes. It must have the ability to control light and temperature, provide a bed or at least a reclining seat if it's a shorter break, and access to food and drink. The goal is verifiable physiological recovery. If the environment fails those standards, the clock keeps ticking, and the pilot will time out before they can fly home.
Okay, but let's talk about the chaos factor. Because aviation is regulated, but the weather is entirely unpredictable.
Always.
Let's do a worst-case scenario. A pilot is sitting on the tarmac at Heathrow. Huge thunderstorm. Air traffic control delays departures for 2 hours. The pilot looks down and realizes they are 15 minutes away from hitting their absolute legal duty limit,
Right.
but they're number 2 in line for takeoff. Do they just turn to the co-pilot, shrug, shut down the engines, and say, sorry, folks, back to the gate, the law says my day is over?
This specific scenario is why the concept of commander's discretion exists. Regulators know unforeseen things happen. If the flight was legally dispatched and the delay happened after the crew reported, the commander has the legal authority to extend the flight duty period
By how much?
by up to 2 hours, or 3 hours if they have an augmented crew with relief pilots on board, so they can complete the flight.
That feels like a massive amount of pressure on the pilot in that exact moment.
It is a delicate psychological tightrope. The commander has to honestly assess their own fatigue and their crew's fatigue. Just because you legally can extend the day by 2 hours doesn't mean you should.
Right. If you're already wiped out, pushing it is dangerous.
Exactly. And importantly, airlines cannot use commander's discretion as a scheduling tool. You can't plan a route that requires discretion just to make the timetable work. It's strictly a tactical buffer for actual emergencies.
And there are consequences for using it, right? You can't just borrow energy from tomorrow without paying it back.
The biological debt must be paid. If a commander extends a duty period, that extension has to be compensated with extra rest later. Usually, the next minimum rest period is increased by 2 to 4 hours. You push the battery past its limit, you leave it on the charger longer.
Okay, so we've got a rested crew within their legal limits. The plane is tracking properly. Now we have to actually fly the thing. And reading the sections on aerodrome operating minima, honestly, it sounds terrifying. Taking off and landing in terrible weather.
The operating minima are the absolute intersection of environmental hazard and aerodynamic capability. These are the baseline weather conditions needed to legally even attempt a departure or an arrival.
And taking off isn't just pushing the throttles forward. Most passengers think takeoff is the easy part. You go fast, you pull up. But the regulations are built entirely around the worst possible thing happening at the worst possible millisecond.
Yes. Let's unpack V1.
Right, V1. What exactly is that?
V1 is the critical decision speed during the takeoff roll. Everything hinges on this velocity. As the plane accelerates down the runway, its kinetic energy increases exponentially.
Okay.
If an engine fails or something systemic happens before reaching V1, the pilot must aggressively abort the takeoff. They chop the throttles, apply maximum brakes, deploy spoilers, and thrust reversers.
And the math guarantees they'll stop in time.
Exactly. The takeoff minima and runway length calculations guarantee that if you abort before V1, you have enough pavement left to stop safely without, melting the brakes or skidding off the end.
But what happens if the engine explodes a split second after V1?
Once you pass V1, you are committed to the sky.
Wow, even with an engine on fire.
Even with an engine on fire, you no longer have enough runway to stop safely given the kinetic energy you've built up. If it fails after V1, the pilot has to continue the takeoff, lift off using the remaining engine, and clear all physical obstacles in the departure path.
That is intense. So when we talk about low visibility takeoffs LVTO, where the fog is so thick you can barely see the nose of the plane, how does that affect the V1 decision?
It radically increases the danger. In an aborted takeoff at high speed, the pilot needs visual cues to keep the aircraft perfectly centered while applying maximum braking.
Right, you don't want to veer off into the grass at 150 miles an hour.
Exactly. If visibility is down to 150 meters, staying on the center line while decelerating a 70-ton machine is incredibly difficult. That's why LVTO requires specialized training and specialized runway lighting.
I noticed the metric used for this visibility isn't a standard weather report. It's called RVR, Runway Visual Range. What's the difference?
Standard visibility is a human observation. A meteorologist looks out a window and guesses how far they can see a building.
Okay.
RVR is a highly precise, localized mechanical measurement. Airports have these devices called transmissometers installed right next to the runway. They shoot a beam of light across a specific distance and measure exactly how many particles of fog, rain, or snow block that light.
So it's not a guess.
It's not a guess. RVR tells the pilot exactly how many meters of the actual runway pavement they will see from the cockpit.
That precision is amazing. But the manual also outlines this fascinating trap regarding takeoff minima. It's the concept of the takeoff alternate. It essentially says that just because you are legally allowed to leave an airport doesn't mean you're allowed to come back.
Landing an aircraft requires significantly better visibility than taking off. You need to see the approach lights and the runway threshold to touch down safely.
Right.
So you often get a scenario where the weather at your departure airport is, say, 200 meters of visibility. That's
Ooh.
above your takeoff minimums you can legally depart. But the landing minimum for that same runway might be 550 meters.
Oh, so if you suck a bird into the engine right after liftoff and you need to make an immediate emergency landing, you are locked out of the airport you just left.
Exactly. You're flying a broken plane in thick fog with nowhere to land.
That's a terrifying trap.
And regulators will not allow an aircraft to launch into that trap. Before the brakes are released, if the departure weather is below landing minimums, the crew must legally designate a takeoff alternate aerodrome.
So a backup airport.
Right. And for a twin-engine aircraft, this alternate must be within 1 hour's flight time. Crucially, that hour is calculated based on the one-engine inoperative cruising speed.
That is incredible risk mitigation. You're not just picking a city on a map. You're calculating the degraded speed of a crippled aircraft, drawing a 1-hour radius based on that slow speed, and making sure a safe harbor exists in that circle.
It's an environmental safety net built purely out of performance mathematics.
Man. Okay, so we've departed, we've navigated the route, we arrive at the destination, now we face the approach and landing. And the evolution of how pilots do low-visibility approaches really stood out.
The transition from the old method to the modern standard is a massive leap in safety.
Let me try an analogy here to contrast the old way versus the modern way, the CDFA, which the manual really pushes. The old method used a minimum descent height, an MDH. I picture this like being blindfolded at the top of the staircase. You walk down the stairs until you hit the lowest safe altitude, the bottom of the stairs. Then, still blindfolded, you wander down a long, dark hallway with your hands out, flying perfectly level, hoping you bump into the front door before you hit a wall.
That is a very accurate description of what the industry called the dive and drive technique.
Dive and drive.
Sound safe? It wasn't great. You descend to the minimum descent height as quickly as you safely could, and then fly level. You apply power, dragging the aircraft through the air at a low altitude.
Just waiting to see the runway.
Right. You stay there until you either see it or hit the missed approach point. It kept you clear of radio towers, but aerodynamically, it was awful. You're low, slow, burning massive fuel. And when you finally spot the runway, transitioning from level flight to a descending landing flare required a dramatic change in thrust and pitch.
Sounds incredibly unstable. So the modern method, the CDFA continuous descent final approach, replaces that dark hallway with a decision height, a DH. To me, this is like sliding smoothly down a long, perfectly angled banister.
Okay, I like this.
You're on a constant glide path. You slide down at a steady rate, and when you hit the exact bottom of the banister, the decision height, you take off the blindfold. If the door is right there in front of you, you walk in. If it isn't, you instantly abort. No wandering in the dark.
The CDFA technique absolutely revolutionized approach safety. By maintaining a constant 3-degree descent angle, the aircraft is in a stabilized energy state. The engines are spooled up to a consistent low-thrust setting. The configuration doesn't change.
And when they hit that decision height?
On a standard Category I instrument landing system that's 200 feet above the ground, and the transition is binary. They look up. If they have the required visual references, the approach lights, or the runway threshold, they continue that exact same trajectory down to the pavement.
And if they don't see it?
They immediately execute a missed approach, instantly.
No hovering, no dropping down another 50 feet, just to take a quick peek through the clouds.
None. The physics of a commercial jet don't allow for hesitation at 200 feet. It takes several seconds for massive engines to spool up from idle to full thrust. If you wait until you are 50 feet off the ground to decide you can't see the runway, by the time the engines make enough power to climb, you've already hit the ground.
Wow.
The decision height is a rigid, mathematical hard stop. It keeps the aircraft out of the dirt.
So we've threaded the needle of the weather, but none of this matters. The tracking, the rested pilots, the stabilized approaches, if the physical energy of the aircraft runs out. The engines need fuel.
And fuel policy is one of the most contentious parts of flight planning.
It seems like it.
Yeah.
Because fuel isn't just filling up a tank like at a gas station. It's a complex legal calculation. And there's this massive economic friction built into it, right?
Oh, absolutely. That friction defines modern flight planning. Aviation fuel is incredibly heavy. Every extra kilogram of jet fuel you pump into the wings requires the engines to burn a fraction of a kilogram of fuel just to carry that added weight.
It's a compounding penalty.
Exactly. The airline's accountants want the aircraft to be as light as possible to save money. But the safety regulators want the aircraft loaded with buffer fuel to handle emergencies.
Naturally.
The EASA fuel policy is the legal compromise between those two opposing forces. You never simply carry just the fuel required for the trip. The total fuel load is a nested series of specific calculations.
Okay, let's break down those nested categories. The first layer makes total sense. Trip fuel.
Right. Trip fuel is the calculated amount to get from your departure runway, climb to cruise altitude, fly the route, descend, and execute an approach at your destination. It assumes normal, planned conditions.
But normal conditions are kind of a myth, right? The atmosphere is chaotic.
Exactly, which is where contingency fuel comes in.
I view this like calculating water for a hike across the desert. You look at the map and say, okay, 10 miles, I need 1 gallon of water. That's trip fuel. But you know the map might be wrong, or the sun is hotter than forecasted, or maybe your bottle leaks a tiny bit. If you only bring exactly 1 gallon, any minor deviation means you die of dehydration. You have to bring extra just for the unknowns.
That is precisely the function of contingency fuel. It is an allowance for the fiction of reality. In aviation, that friction is usually unexpected headwinds that slow your ground speed, forcing you to fly longer.
Or air traffic control holding you lower.
Yes. If ATC can't clear you to your efficient cruising altitude of 35,000 feet due to traffic, they hold you at 28,000 feet. The air is thicker there, so the engines burn more fuel. The manual even discusses active management techniques like reduced contingency fuel procedures, where crews constantly recalculate this buffer during the flight so they don't eat into their protective layers.
Okay, so trip fuel gets us there. Contingency fuel absorbs the atmospheric bumps. But what if we arrive and suddenly a massive snowstorm closes the runway?
This is why you must carry alternate fuel. This is a specific block of fuel required to execute a missed approach at your destination, climb back up to altitude, fly to your legally designated alternate airport, and conduct a full approach and landing there.
So you literally have the fuel for an entirely second mini-flight sequestered in the wings.
You do. But the regulatory nesting ball goes one layer deeper. The absolute bedrock is the final reserve fuel. This is the ultimate liquid lifeline. You are legally required to land with this fuel still sloshing in the tanks. You do not plan to burn it under any circumstances.
How much fuel is that?
For standard turbojets, EASA dictates it must be enough to fly for 30 minutes at holding speed, at 1,500 feet above the destination.
30 minutes.
Right. A final, unassailable half-hour buffer to troubleshoot a problem, deal with landing gear, or wait for a runway to be cleared. If a pilot realizes their fuel state is going to drop below this final reserve amount, they are legally required to declare a fuel emergency, a mayday.
And that gets them priority.
Absolute priority over every other aircraft in the sky.
That structural redundancy is amazing. But this brings up an edge case scenario I found fascinating in the docs. The isolated aerodrome.
Yes.
Because what if you're flying somewhere incredibly remote, like an island in the middle of the Pacific Ocean or some research station in Antarctica? There literally is no alternate airport for thousands of miles. How do you calculate alternate fuel when there is no physical alternate to fly to?
The isolated aerodrome procedure is a massive divergence from standard policy, and it requires specific, competent authority approval. You can't just declare a destination isolated because it's convenient for the airline.
Right. We just don't want to carry the weight.
Exactly. They won't let you do that. But in these specific cases, because flying to an alternate is geographically impossible, the operator is permitted to carry what is known as holding fuel instead of alternate fuel.
So instead of packing fuel to fly away to a different city, you just pack a massive amount of fuel to fly in circles above the island.
Essentially, yes. The legal and meteorological assumption underpinning this rule is that even the most severe localized weather systems, the kind of intense squalls that would prevent landing, are transient. They move.
Right.
If you carry enough holding fuel to simply wait out the storm, usually an hour or two of extra loiter time, the weather will eventually pass, visibility will improve, and the runway will become available.
It's basically a calculated high-stakes bet against the weather, backed up by just tons of reserve kerosene. It's fascinating how every single drop of fuel is accounted for and protected.
The entire system we've discussed today, the fuel policies, the weather minima, the fatigue limits, the automated tracking, it's all a testament to how the aviation industry learns. Aviation regulations are often described as being written in blood.
Written in blood. That's a heavy way to put it, but it's true.
Every rule we covered was drafted in response to a hard-learned lesson, an accident, or a critical vulnerability. The operational architecture exists to trap human error and mechanical failure before they compound into a catastrophe.
Well, we have definitely unpacked the invisible scaffolding that supports every single commercial flight today. I mean, we started with the immense responsibility of operational control and how the shadows of past mysteries forced the implementation of automated tracking systems that report a plane's location no matter what.
Right.
And we explored the deep biological science behind flight time and duty limitations, realizing that airlines aren't just scheduling employees, they're actively managing the degradation of human cognition, fighting against that circadian whiplash.
And we translated the environmental hazards of flight into pure physics, examining the violent kinetic energy of a V1 engine failure and the elegant mathematics of a continuous descent final approach down to a rigid decision height.
And finally, we saw how the physical energy of the aircraft, the fuel, is basically weaponized against uncertainty, providing trip coverage, contingency buffers, and that final untouched reserve.
Yeah.
So the next time you, the listener, are sitting in a terminal, frustrated by a rolling delay or a sudden diversion, maybe you'll look out the window with a completely different perspective. You'll know that the delay isn't just an inconvenience. It is likely a commander exercising their vital legal discretion, or a safety management system protecting a pilot's biological battery, or a localized RVR sensor protecting you from a terrifying, low-visibility approach.
The frustration of a delay is temporary, but the uncompromising rigidity of the safety architecture is what makes commercial aviation the safest mode of mass transport in human history.
It really is. But before we wrap up this deep dive, I want to leave you with a provocative thought about where all of this is heading. We spent a lot of time discussing the human element, the commander's discretion, the physiological limits, the visual identification of the runway.
Biological factors, yeah.
Right. But as we look to the near future, aircraft are becoming staggeringly automated. They track themselves with pinpoint satellite precision. They manage their own fuel flow. They can practically land themselves in zero visibility conditions using advanced auto-land systems.
It's true, the technology is advancing rapidly.
So as these algorithms become infinitely smarter, faster, and more capable of processing vast amounts of data without ever suffering from fatigue or circadian disruption, we have to wonder about the future of authority. Will the commander's discretion, that ultimate authority to push past a weather minimum or extend a duty limit, remain securely in the hands of the biological pilot sitting in the cockpit? Or will those life-and-death split-second calls eventually be made by an unblinking, untiring algorithm sitting in a server farm thousands of miles away? Will the human pilot eventually become just another backup system monitored by the machine? Something to ponder on your next flight.